Hi everyone, I'm Alice, education lead at ZKM. The ZKM team recently announced Ziren, which is our newest release of our ZK VM. So in today's video, we'll be going through some details of what Ziren enables, and we'll be doing a walkthrough of how you can get started with Ziren using the project template. So first, going into some details about what Ziren is. Ziren is ZKM's most recent ZK VM, formerly called ZK MIPS. It has the features from the ZK MIPS version 1.1, but also including GPU acceleration as well as a distributed proving network for network-based proving, which is an alternative to local proof generation. And we also have introduced some other optimizations for overall faster and cheaper proof generation. So Ziren is built on the MIPS ISA, and also the main use case the team is building are entangled rollups, basically enabling cross-chain messaging and interoperability using ZK proofs, but without having to implement the actual architecture of a bridge, which has its own trust assumptions and may potentially introduce some security vulnerabilities as well. So the first L2 that's part of the entangled rollup network is Goat Network. Goat Network is a Bitcoin layer 2 that utilizes proofs that is generated by Ziren. Ziren is also listed on ETH proofs, so you can track our progress towards real-time proving there. Some recent optimizations resulted in doubling the total proof throughput and also reducing the block state preparation time from 5 minutes to just under 30 seconds. So we're on our way towards real-time proving. And with GPU acceleration capabilities added onto this new release, we were able to see around 30 times faster proof generation for core proofs. And also with this new release comes new optimizations around the constraint system, a new tool train that adds to the overall dev experience, full ECDSA precompile support, and also just Ethereum native compatibility for digital signatures. These all contribute to fast proof generation time and also improved DevX on the tooling side. Now, going into the walkthrough portion, we'll be going through step by step on how you can generate and verify your first proof with Ziren using the project template. As a first step, you should install the Ziren toolchain using this command over here. That toolchain will allow for you to complete actions, including executing your program, including proving and verifying, all from the command line. And the next step after you have your toolchain installed is to clone the latest version of the project template. And the link to the project template is over here. And then I also linked down below the installation guide and the quick start guide within our docs for more details on different options to installing the toolchain. So you can either do it through the quick install option over here or build it directly from source. And then there's some other details like some hardware requirements and also the Rust version that you need. And also for the quick start, it's just a complete guide for completing all these steps we're about to go through just in written form and in more detail. So if you're doing this on your own and if you need more information, be sure to check out these two guides. Now, when you clone the project template, you'll see three main directories. There will be a guest directory, a host one, and also a contracts one. The guest and the host directories hold the guest and host Rust programs for proving an example. That example is proving the execution of a Fibonacci sequence. And remember, your guest program will contain all your core program logic to be executed inside the ZKVM. The host program itself is what's executing the guest program, and that controls just the end-to-end process of compiling and executing its corresponding guest program, generating that proof, and then outputting any verifier artifacts for later verification. And the contracts folder will contain solidity contracts for on-chain verification of the Fibonacci program, as well as some test scripts. So that's why we recommend for developers to just clone the project template because it includes these pre-made contracts, as opposed to the other option, which is directly making a new project from the command line. So with the project template, you are included with all of these, including your guest and host programs, some test scripts, and then the Solidity contracts. It's like an all-in-one package here. And you can, of course, change the contents in the host and guest programs to fit your use case. Instead of just the Fibonacci example, we'll just be sticking with that example for this walkthrough. And the overall pipeline is as follows. First step is to build your guest program to generate the ELF. The ELF is the executable that the program is compiled to that the ZKVM will use to generate a proof for. And after you build your guest program, there's a couple of options you can go through next. If you just want to test your program to see if you're getting the right outputs, the expected outputs, without generating a proof and spending the time and resources to do so, you can just simply execute your guest program and it'll just have the outputs that are generated without the proof. And then if you then, after testing your program, you want to generate some proofs, there's a few different types that you can choose from. There's the core proof, that's by default. And we also have compressed proofs. These proofs are constant in size. It's ideal if costs are a concern for you. And there's also EVM compatible proofs, which includes both Plonk and Grot16 proofs. Now it's required for you to generate a proof that is EVM compatible if you're trying to do any sort of on-chain verification, which is what we'll be doing in this example. The Grot16 proof is recommended. You could also generate a Plonk proof. Compared to the Grot16 proof, it's larger in size, but it doesn't require a trusted setup. So we'll be generating a Grot16 proof for the Fibonacci program in this example. And then later on, we can do on-chain verification of the proof via a verifier contract that's included in the project template. So that's an overview of what we'll be doing for this walkthrough. So when you open the project template after you clone it, this is what you'll see. We can take a deeper look at the guest and host programs that are part of the template. So if you go to the guest directory over here, you go to this main program. This main guest program will encode the program logic for proving the Fibonacci sequence. So over here, these are just some directives to make the Rust program compatible with the ZKVM. In this line over here, within the main function, we're first reading an input n from the host. And then next up, we are computing the n-1th and also nth Fibonacci numbers assigned to A and B using this Fibonacci function from a crate that we're using. And then as our next step, we will encode all of the public values of the program. And then finally, in this last line here, we are committing the output bytes to the ZKVM's public output, and that allows the verifier to validate that the outputs are indeed matching. So that's for the guest program. Taking a look at the host, which will be under the host directive in this main file. And remember, the host will execute the logic that is held in the guest program. So over here, as this first kind of step, we're including the compiled Fibonacci guest ELF binary for compilation later. And The guest program is basically compiled into the MIPS executable ELF through this program over here, also under the host directory, this build program. And every time the build program runs, an ELF will be generated, and that generated ELF is stored in this target folder over here under ELF compilation. And that is just some details about generating the ELF. Going back to the main file within the host program. Over here, moving on, these are just the command line arguments that we'll be using. So either execute, core compressed proofs, and then this n is just our input for the Fibonacci number that we'll be computing. Over here, we're just setting up the logging, loading any variables that we have from our environment file, parsing any command line arguments, enforcing that one mode is chosen. So either the core compressed EVM compatible mode. And then over here, just setting up the prover client, setting up the inputs, writing that input n for the guest to read. And then we're going on to the next part, the execution mode. So over here, we're just executing the program or the ELF. And then as kind of our next step, we're running the guest program inside the ZK VM without generating that proof, just capturing that output and reporting it. That's only if the user selects the execute mode. And then as our next step, we're just reading the output decoding from the guest. And then basically over here, we're just validating that output correctness by recomputing it locally and comparing it. Over here, just printing the number of cycles. That's very helpful if you're curious about how many cycles that took for that computation to run. And then over here is just going into the proving mode. So we're just setting up the program for proving if the user selects any other option besides the execute mode. And over here, setting up the proving and verification keys from the ELF. And then these are just the lines to generate the core proof and also the compressed proof right down below. And then eventually we'll get to verifying the proof using the verification key that is generated in the process. And then it ends if that process is successful. So that's just an overview of what's included in the host and guest programs. And again, you can tailor these programs to your choosing depending on the use case you want to run. Okay, so now that we have that overview, we can go ahead with the walkthrough. After you have your ELF, you can execute your program first without generating that proof. Just go into the host directory and then run cargo, run release, and then execute. And then it may take some time to compile. I've previously compiled this, so it'll take a bit shorter. But over here, we can see that as part of our program, we specified sample public input. You can change this on your end, but for just by default, that sample public input was assigned n/20. And so we're computing the 19th and the 20th Fibonacci number, which will yield these outputs. And our output values are indeed correct. And then we're also outputting the number of cycles that was used. So now that we confirmed that our logic is working from our program, we can now generate our EVM compatible Groth16 proof. So the command that you'll be using for this is just cargo run release bin EVM, and then specify that the system is Groth16. And if you want to generate a Plonk proof instead, just replace the Groth16 with Plonk. And in the quick start guide that I previously linked to an earlier slide, you can find some of the other commands if you want to generate non-EVM compatible proofs, including the core and compressed proofs. But over here, depending on the hardware of your machine and if you're using local or network proving, right now I'm just using local proving. This may take some time. I won't run through the full proof generation just to save time for this video. But when you do, the output should include your public values that you specified. In this case, our public value was 20 that was assigned to n, and then also the verifying keys and proof bytes. So I'm just going to stop this for a second. An example output would be something like this. This was a Groth16 proof that I generated prior to recording this video. But essentially, you'll get some data of how long each step took, including how long, for example, the proving key took and the witness file. And then eventually, as your output, you'll be getting over here some values for your verification key, for your public values, and then also the proof bytes. And that's what you should be getting just as a result. And all of those kind of data will be put into the proof fixtures. So if you go under contracts, and then you go to the fixtures directory, since we generated a Groth16 proof, all of that data will be held in the Groth16 fixture JSON file in JSON format. And as you can see, it includes all of our public outputs, the proof itself, and also the verification key that we'll be using later on for verification. And that is just what one example of the fixture would look like for the Groth16 proof. Now, local proving is enabled by default. So if you go to your environment file, for example, over here, it's local by default, but it is recommended that you use ZKM's prover network for any type of heavier workloads. You can go to zkm.io /apply to apply to be whitelisted and adding your address to the whitelist to access the prover. But to enable the network proving, you can update this file, just specify network instead of prover, and specifying some more information like your private key and the path to your certification key as well. That's just some more details if you're interested in using network proving. But going back, once you've generated your proof, you can then go on to the next step, which is compiling the verifier contract. And then we can first compile and execute all of our Solidity test files that's provided by Foundry in our contracts directory. We're using Foundry, so make sure to install that beforehand. So we'll just go into the contracts directory and use forge test as our command. Basically, Foundry will detect and run all the test contracts to verify that the proof fixtures, which we previously saw under our contracts directory, are correctly accepted or rejected. And then also the Solidity verifier file contracts. So that includes the ZKM verifier Grok 16, and then also if you are using the Plonk, it will be the ZKM verifier Plonk files. If those Solidity um, files behave correctly. And then there's also an application contract over here that's generated just for this Fibonacci example, if that is integrated correctly with the verifiers. So those are all of the tests that Foundry will be detecting and running through. And then as you can see, we ran a couple of tests using some test files that were already made under the contracts, and you can make your own test files as well. So all of the tests were successful in this example. So now that we have completed that step, we can move on to our next step, which is deploying your verifier contract directly to some EVM compatible test network. In this example, we will be using Sepolia. And we'll be using this command over here, this forge script, specifying over here that we're trying to execute this ZKM verifier Grok 16 script, which will deploy this ZKM verifier Grok 16 contract to the network. And as your parameters, you should specify the and your RPC endpoint. So for example, you could get it from Alchemy or Infura. I'm using one that I created from Alchemy for Sepolia. And then also providing your private key of your wallet. So I'm just using this test wallet with some Sepolia ETH on it. And then specifying broadcast so that this can be broadcasted to the network and you'll be able to verify it using a transaction hash. And if you want to deploy this to a different verifier, like for example, if you generated a Plonk proof instead, just change, it's the exact same command, but just change from Grok 16 to Plonk, and just replace the script name. So running this command, we can see that we are currently waiting for pending transactions and having this be deployed directly on Sepolia. And as a result, we'll see that our success hash is outputted. And you can view this directly on Etherscan. You can also view the new contract address that we created. So that concludes the walkthrough. We were able to, using the project template, we were able to build our program and generate the ELF. We were able to generate an EVM compatible proof, verify it, and deploy it on a verifier contract on Sepolia. So hopefully that gives a good overview of what you can do with the project template. And again, you can always tailor it according to the use case that you want to build on Ziren. But just going back to this presentation over here, just some more announcements, related matters. We have our Ziren Developer Series that will be coming out soon. This is for all developers who are interested in building with Ziren. We'll go through the architecture details in our ZK VM, some available tooling and resources that are available for you guys, and then some example walkthroughs of some fun use cases. And if you want to read more about some of the announcements that came with the Ziren release, I linked some of our articles over here. And if you want to start building, I also linked the Ziren repo over here, as well as our docs, and we'll be adding more to our docs in the coming weeks. But let us know if you have any questions, and happy building.